Good afternoon. My name is Julien. It's my first time in Poland. What took me so long, right? So super happy to be here today. This is a pretty cool subject. So let's get started right away. And I'm going to talk about deep learning for a bit. And then we're going to try some demos. And if the demo gods are with me, they're going to work. If not, you can throw stuff at me. I'm used to it. Let's go. So here's the agenda. We're going to talk very quickly about AI and the story so far. Then I'm going to show you very quickly a few applications of deep learning technology. Just a few things that you can do. And then we're going to dive into the topic of today, which is Apache MXNet, which is a deep learning library for to build neural networks, train them, and use them in your applications. So I'll talk about MXNet a little bit, show you some of the key parts of the API, and as fast as possible, I want to show you some code and run some demos, because this is how you really understand how to work with MXNet, okay? So AI, the story so far. So this is AI, right? Do you remember when that movie came out? Most of you were not born, I'm afraid. All right. It came out in 1969, right? 2001: A Space Odyssey. And most of us, well, a lot of us have been obsessed with this movie. And I've been obsessed with building HAL, right? Building that artificial intelligence that you can talk to, that can talk back at you, and do some complicated stuff, and hopefully, fail to kill you, right? That's the part we'd like to forget. And for decades, people have been trying to build systems like this, right? And artificial intelligence is maybe something you studied at the university. And when I was there a century ago, they would tell us, yeah, AI has been around since the 50s, but it's very cool, but you can't really do anything useful with it. So it stays in the lab, and that's it. And that's a sad story. All right, fair enough. So what happened then, right? Actually, in 2001, the actual year 2001, Marvin Minsky, who is one of the founders, one of the fathers of AI, and he actually was an advisor to Kubrick on the movie. I don't know if you knew that. He wrote an article saying, hey, it's 2001, where is HAL, right? 50 years after artificial intelligence was invented, we're still very far from having something remotely as smart as HAL. And he listed a number of reasons why this failed to happen. That was 2001, right? So today, it's 2017, and we still have no HAL, and I'm still wondering why. Because on the other hand, everybody is doing machine learning, right, today. Most of you are doing machine learning, either as a service, or you're building stuff with Spark and open source libraries, etc. So machine learning has never been so powerful, and it's never been so successful as today. But then how could machine learning be so successful and AI be so terrible, to be honest? Well, it's because traditional machine learning doesn't work when you're trying to solve problems where features cannot be explicitly defined. Okay? Let me take an example. If you take weblogs, and you're trying to use those weblogs to predict on what page or what ad a user is going to click. Well, you look at what's in the weblog, okay, and it's pretty obvious what's in there, okay? Time and date and user ID and URL and user agent and tons of things. So you have to find the ones that are meaningful to build your prediction model, but at least you get to pick your features from a set that is very well defined inside your log. Now, imagine you're trying to recognize images. So I'm giving you an image that's 1,000 pixels by 1,000 pixels, okay? And I want to know if that's a dog or a cat or a tiger or a bottle of wine. So that's 1 million pixels. Is every single pixel a feature? Which are the pixels that really make sense? As you can see, compared to the 10 or 20 features that you typically use with machine learning, it's a very different problem to solve. And so that's why traditional machine learning has not worked, and still does not work to solve problems where features are so many and so complex that they can't be expressed. So the problem we have to solve is how do we get that knowledge into a computer, right? Without explicitly expressing features. And well, to do this, we have to go back to something that is very old when it comes to computer science. And of course, I'm talking about neural networks. Neural networks have been there since almost the 1940s, right? And the first few major breakthrough came in the 50s. So it's literally 60 years ago, right, that this technology has been invented. And like I said before, it's been there forever, but until very recently, it did not deliver the goods. Okay? Why? Mostly for two reasons. Because back in the 50s and 60s and 70s and 80s and even maybe the 90s, we did not have very large data sets. Okay? So in order to train a neural network properly, you need tons of data. The more data, the better. So if you don't have lots of data, then training is not going to be very good. The second thing is, even if you had a bit of data, you needed a lot of computing power to train the network, right? Those are very CPU-intensive operations, lots of math operations. And on CPUs, especially older CPUs, that wasn't possible at all. So those two problems are the reasons why neural networks did not deliver back then. Of course, now it's quite different because we have huge data sets, right? All of us are generating tons of data on mobile phones and web and video and mobile gaming and everything. Everything we do now ends up in the log somewhere, right? And there are large public data sets like ImageNet or the YouTube data set, and even on AWS we host some public data sets for everybody to consume. So data sets are large and they're available. And thanks to GPUs, we have a ton of processing power, right? Recent GPUs have thousands and thousands of cores on one chip, right? So when you have multiple GPUs in one server, that's a crazy amount of processing power, okay? In just one server. So computing is not really a problem anymore. Data sets are not really a problem anymore. So now we have all that we need to train those neural networks and to build cool stuff, right? And we can do it cost effectively thanks to the cloud, because we can grab all the resources that we need in the cloud, all the GPU instances that we need to collect everything, to compute everything, and generate some results. And when we're done, we can release all those resources and stop paying for them, right? So the scalability and the elasticity are very important. And once you have the model ready, actually you can use it on something that's very small, okay? Using a deep learning model, you can do it on a Raspberry Pi, and we'll try to do this later. Okay, so for the last few years, this is why you've been hearing every single day of deep learning and AI, and it's not a buzzword. Those multiple factors now make deep learning a reality, and people can use it cost effectively to build very, very smart applications. So let's take a few examples. Every year, there's a challenge for research teams, which is called the ImageNet Challenge. It's based on the ImageNet dataset that I mentioned. And basically, they have a whole lot of images that they need to sort, that they need to identify according to 1,000 categories, okay? So let's take an example, right? This is an actual image in the dataset, 2 images actually. So who thinks this is the same breed of dog? Come on, take chances. All right. Who thinks this is a different breed? All right. Who has no idea, even if I gave you 10 minutes to figure it out? Okay. So that's the challenge that is thrown at those deep learning models, okay? So 1,000 categories, and you have to predict 5 categories for each image, and if the right one is in the 5, then it's considered a success, okay? So for the record, this is not the same breed. Don't ask me why. You know, I was in Stockholm not so long ago, and they're supposed to know about those things, and they couldn't explain it either, so I don't feel too bad, okay? So every year we have this competition from 2010 to this year, and the blue line is the error rate, okay? So we go from 28% mistakes down to 25, down to 3 last year, okay? 3% error rate for the best network. And the red bars are the number of layers in the network. So we go from 1 layer to 8 to 19 to 152 to 269. Can you imagine that? That's what it's called. That's why it's called deep learning, right? 269 layers in the network. Okay. So, do you want to guess what's the error rate for humans? All right. Who says more than 10%? All right. Who says less than 3? All right. Who says between 5 and 10? All right. Yeah, so you're pretty close. For humans, it's 5.1. Okay? I would say not all humans are created equal, probably, and especially if you do the test on Sunday evening, or, you know, might be different. Anyway, a normal human in a decent state does 5%. So, well, the good news, or is it a good news or bad news, you decide, but computers and models are better now than us at recognizing complex images. Okay, that's a significant difference, and they keep improving, right? So within seconds, less than a second, they can accurately classify millions of images in 1,000 categories, animals and plants and objects, etc. I think that's pretty impressive. Well, this one here, I'm sure you've heard about it, and you know, I met some of my colleagues here who are contributing technology to this. So some of it is actually, you know, built in Poland. So congratulations. That's the Echo device, and I love to describe it as a mic and a loudspeaker, and people hate it when I do that. But this is mostly what it is. But of course, it's connected to the cloud, and it can do natural language understanding, and speech processing, and text-to-speech, etc., etc. And I mean, I'm sure you've seen this, maybe on YouTube or on videos. And you know, the quality of the voice is very impressive, and the quality of the interaction is pretty impressive. And all that stuff is based on cloud-based deep learning technology. Okay, so it's in everyday life, right, that we use deep learning now. Okay, let's talk about MXNet. So MXNet is it's an open source library for deep learning. It was accepted into the Apache project, so that's good news, because it means, you know, it belongs to everyone right now. It's not driven by a single company. And it's, as you will see, it's fairly easy to use. It supports multiple programming languages, and it's quite scalable. And this is one of the reasons why we picked it as our preferred library in AWS. So this is, you know, scaling on multiple GPUs in the same machine, right, from 1 to 16. Okay, so running training on different models, well-known models. And so the red line is the ideal line. Okay, so it's a linear scaling. So I know it's not a straight line, but that's because this is not a linear scale, okay? To make the graph actually visible on the slide. So the red line is linear scaling, and as you can tell, for some of the models, we get pretty damn close to linear scaling. And if you go beyond 16, oops, sorry about that. If you go beyond 16, up to 256 GPUs running on many machines, on many servers, Well, you can see that this trend continues, right? So MXNet scales almost linearly up to 256 GPUs, and I'm quite sure, if someone was willing to spend the money to go to 1,000 GPUs, we would see that trend continue. So it's important when you want to train very large models that could last for hours or days or more. If you want to get things done faster, you can add more GPUs and you will reduce linearly the time that it takes. So let's look quickly at some of the important symbols, some of the important objects in the API, and I'll show you some code. So training models is always about three things. It's about defining data, right? And if some of you have done data science, you're used to doing that. Maybe you do. Maybe you use NumPy or similar libraries in Python. You build multi-dimensional arrays where you put your input data. Well, MXNet has the same thing. It's called the ND array. Stands for n-dimensional array, where you're going to put your data, right? Your tensor. And then we have symbols. Symbols is how we define the networks. So basically, we build a graph connecting with nodes and layers connected to one another. Okay, and the cool thing is we can build graphs without having to specify what the data is. There's a very clear separation between how the data looks, what the actual data looks like, and how the graph looks. So you can build networks that will apply to any kind of data. And the third thing is the module where you put the two together. And you say, well, that's my actual data, and this is the model. This is the network that's going to be trained on that data, and this object is called a module. Okay, and you will see that in the code in a few minutes. Then, of course, we have tons of functions to help you load data, from well-known formats like images and so on, to make your life a little easier. Okay. If you want to know more about this, this URL is a blog article that I wrote a few weeks ago as an introduction to the API. So feel free to go and look at this. I go real slow, unlike today, and you can really do it, as slow as you need and understand every single detail. And so, on top of this API, to build everything, you have higher level APIs that allow you to build full networks, complete networks, in just a few lines of code, right? You don't have to define every single neuron and connect everything. If you want to define one fully connected layer, well, you just use that fully connected API here. If you want to define a convolution layer for a convolutional neural network, you can use that convolution API. So you have helper functions that help you define networks in just a few lines, like you will see in my examples. And using that, of course, you can throw images and video and sounds and text, etc., any kind of data with the right model. And you can do all those funny examples that you've seen, image detection, image segmentation, and machine translation, etc., etc. MXNet provides all the APIs to do this and to build the networks to do this. Okay? So before I go into the demo, you will get the slides, of course. We have a few more resources to make your life easier. So we have built a deep learning AMI, so an Amazon Machine Image. Okay? If you're not familiar with AWS, basically it's the binary file that is used to launch virtual machines. So we pre-installed it. We have one running on Amazon Linux and one running on Ubuntu with all those tools and all those frameworks installed. So basically you just start that AMI and you have MXNet and TensorFlow and all the other ones installed. And you can start working right away, right? You have the CUDA drivers, so you can use the GPUs on GPU instances, etc. So if you try it out, it's going to make your life much easier. And there are quite a few blog articles and additional information on our websites, but you can look at those links. Okay? So, we help you get started with the AMI and some documentation. And my blog posts, of course. So here's the first demo. So the first thing I'm going to do, I'm going to train an MXNet model on a data set called MMist. So MMist is a set of 60,000 handwritten digits right? Written by different people. So they look like this, right? And each digit is a 28 by 28 pixel grayscale image, right? And so we can translate it easily to a matrix, right? And this is what we're going to load in the ND arrays. Okay, want to do this? Go. Can you read in the back? Wave if you can read. Right? Thanks. Help me here. So let me show you quickly what the code looks like. And again, I will go a little bit fast, but this is explained in my articles. So here, basically, I'm loading the data, right? I've got those images in files, and I'm loading them in what we call an iterator, which is similar to iterators in other languages. An iterator is going to serve those samples batch per batch as we go into the network. Okay? Then we define our network. Okay, so we have the input layer with the data, and we have a first fully connected layer, and a second fully connected layer, and the output layer. Okay, so I've got 3 layers. Well, the input data and 3 layers in my network. Okay, and as you can see here, I don't have to specify every single neuron and every single tiny thing. In 4 lines of code, I can define my network. Okay? Then, need to go down a bit. Then I'm binding my data, my iterator, to the network that I just created, right? So this is what I told you before. You have the data on one side, you have the network on the other side. And as you can see, when I define the network, I say nothing about the data, right? It could be 28 by 28 images, or it could be something else, right? But we'll figure it out when we put the two together with the module. This is how I say that I want to train on the GPU, okay? That's it. I don't have to worry about anything else. I say, hey, give me GPU 0, and I'll work with that. And then I'm going to train for a few epochs. So I'm going to run the data set a few times, again, through the network. And I'm saving a small part of the data set to do validation and to measure accuracy. And that's it. That's not a lot of code. So let's do it and train it. OK, so I'm loading my images. And as you can see, I'm throwing the 60,000 samples at the network over and over and over and over again. And you can see the training accuracy going up, okay, which shows the network is learning how to predict the correct number from a given image. Okay? And we even get to 1, so we were able to perfectly learn that training set. And when I take my validation set and run it against the model, I get to, maybe you can't really see it, I get to 97.7 accuracy. Not too bad, right? How long did that take? 1 minute? So in 1 minute, I can train a model that is able to recognize handwritten digits. Okay, so let's try it. So what did I do? Well, I took my favorite paintbrush application, and I drew some numbers, right? So this is my handwriting, and you can tell I was quite sober when I did that. And we're going to try those numbers against the network that we just trained. So I'm going to load those images, put them in an ND array, and run them through the network. Okay, and so here, for each image, I see a vector of 10 floats, right? Because I have 10 possible values. A digit could be anything from 0 to 9. So each float is the probability for the corresponding digit. So as you can see here, for the first number is my 0. Well, the network says there's a 99.4 probability that this is a 0. Okay? And as you can see, it gets all of them right, okay, with a very high probability, except the last one. So my ugly 9, the network actually thinks this is an 8, with a 65.9% probability. Okay, so can we build a better network? Yes. So I've got a different network. Okay, so this time it's a convolutional neural network, which is known to be very good at recognizing images. And as you can tell, it's a little bit longer, but it's not a million lines of code either, right? A few lines. So I'm just defining a slightly different network. And here I'm going to run this on 3 GPUs, right, to make it faster. So let's train this. Okay, so same story. Loading the data and showing the input data and the correct value to the network and letting the network learn. Okay? And you can tell this takes a little bit more time because convolutional networks are a little more resource intensive. But we're going to get there. And while it's doing that, I'll check if my little buddy here is still running. It looks like it's running. I think it wants to say something. Can you switch this one on, please? Thank you.
Bardzo szczęśliwy. Życie spotkam. Na zdrowie.
Right. Whatever that means. Blame Google Translate if that makes no sense. Okay. And that's Poly, by the way. It's one of our AI services. And, it's mostly built in Gdansk, right? So we should congratulate your engineers for building this. So training is done. Okay. So training is done. And you can see validation accuracy is 99% this time. So let's try to predict. So it seems to be better. And so now let's predict it. Okay, so same thing as before, my handwritten images. And, okay, that's a 0, and that's a 1, and that's a 2. It gets all of them right. Oh, sorry, I forgot to change my... I'm still using the old network. That's why we... Okay, so now I'm using the new network that I just trained. Okay. All right, so that's a 0, that's a 1, that's a 2, that's a 3, etc. And the 9 is really a 9, right? Even with my very bad handwriting, right? This is a 9, okay? So you can build better networks, train them again, improve your accuracy. All right? So please, I know this is very fast, but it's a short session, so if you want to know more, please go to that to my blog articles. You will get all the details. All the sources are on GitHub, and you can replay all of that. Okay, and now I've got 1 minute left, which I think is what I need. I'm going to try and do this with my friend here. And if you don't work, I'm going to crush you. Okay. Can you see it? Yeah? He's got a Twitter account. So I'll put it here, all right? Okay. So that's a Raspberry Pi with a pre-computed MXNet model. So I trained a model for hours and hours and hours in the cloud, and I copied it in there. And let's see what happens. And to make it even worse, I've got an Arduino here with a remote control. And those things are talking through AWS IoT. Right? So if you're in the back, you want to see this, please, you can come here. OK, so let's try to move it. Hey, you can tell it's moving, right? Yeah? Oh, that's fantastic. Thank you. All right. Can I get that video? All right. Yeah, it could do this, right? All right. Can do a little dance like this. Come on, you're on screen. Do something. All right. OK. All right. OK, so I'm going to cheat a little bit. All right. OK, and if I push that button here,
I'm 88% sure that this is a baseball. The object is 21 centimeters away.
Is it a baseball? Yeah? All right. I'm done. Thank you.